So continuation to same thing. So okay, we are discussing about the impulse momentum theorem. Okay, and we discussed the three questions before that. I'm gonna find out the work done by the spring when it is comes to natural link positions. The like another question they can ask you: find out the work done on the block B when the spring comes to natural link positions. The earlier question was work done by the spring when it comes to natural link positions. This question they are interested work done by the spring on block B when it comes to natural link positions. Okay, so one of the method is that we know the work done by total work done by the spring is half kx naught square, and that is work done by the spring on A plus work done by the spring on B. Okay, and from the work energy theorem we can say the net work done that is equals to change in kinetic energy. So this also we can write in the summation of kinetic energy. We know this part, and earlier we know the rate kinetic energy ratio also we can find out. Since momentum is conserved in this case is inversely proportional to mass, and that is coming out to be 2. So in these things we know the ratio, so we can easily find out kinetic energy by B, basically one third of half kx naught square, that is kx naught square by 6. Okay, so therefore work done by spring on B we can calculate, that is equals to delta kb, that is equals to half kx naught square. Let's move to a new questions. Okay, they are saying there's a wedge, this is my wedge, a block is there that is released from rest. Okay, the wedge is kept on a frictionless floor. The radius of this circular part is given to you r. They are asking you two questions basically here. First, when the block has reached to the bottommost point, then wedge will be displaced something on this direction. Then what is the displacement of wedge as well as displacement of the block when it comes to basically ground? Second thing they are interested ki what is the speed of the block when it comes down. Okay, let's try to solve these questions. First thing, if I consider again, first analyze the question properly first and then we'll move to the solving part. See, this if I consider wedge plus block is my system. Wedge plus block is my system. Then are you finding any external force along the x directions? No, there is no external force along the x directions because it is frictionless surface. So we can say momentum will be conserved along the x-axis. So first thing what we noticed कि F external along the x direction equals to 0. Second thing we understood, initial momentum of the system is 0. System is 0. This implies center of mass will be at rest along the x-axis, yani delta x of Cm will be 0. As well as momentum will be conserved, yani momentum of the system final will also be 0. These two informations we can deduce from the above two equations. Now, they are asking you what is the displacement of the block when it comes to ground. We know with respect to wedge, it will travel x distance along the x-axis. But from the ground frame, we have to add the displacement of the wedge. We can write displacement of the block along the x direction, that is displacement of the block with respect to wedge plus displacement of wedge. Okay, so if I assume the wedge has displaced by x amount in backward directions, then displacement of block we can write, that is r minus x in the forward directions. Now we can use these equations. m1 x1 plus m2 x2, m1 delta x1 plus m2 delta x2 equals to 0. If I use here, so the wedge mass is given to m into x with a minus sign plus small m into r minus x equals to 0. That implies what? If I solve these equations, we get x equals to mr divided by capital M plus small m. What is this x? You should keep in mind this x is the displacement of the wedge which I have said in the backward directions. So let's calculate the displacement of the block that we have already said, that is equals to r minus x. If I substitute this part, we will get capital mr divided by capital M plus small m. Okay, so this part is clear. Now second part, we are interested what is the velocity of the block and velocity of the wedge. Both we are interested in calculate. Let's calculate here. So let me redraw the diagram. This is my wedge. Okay. This is R, this is also R, the center I'm assuming. The block was here initially. Finally, you can say final condition is like this. Just let me copy this part. Finally, the block will reach to this point. During that time, this will gain some velocity. Let's say V, small, capital V. And let's say this has gained the velocity small v. So first thing, we can conserve here momentum. So this is capital M, this small m. So initial momentum was 0, so final momentum will also be 0. So first equation we can write m into capital V is equals to m into small v. That is using the momentum conservation principle. Conserve. Now, since there are two unknowns, capital V and small v, there are two unknowns. So we have to find one more way, one more equation to solve these equations. And that we can do from energy conservations. So we can say initial or work energy theorem, whatever you want to apply. So work done by gravity is mg into small h. Since this block center of mass is at constant, wedge center of mass remains same, so that means work done by gravity on capital M is 0. But if you think about small m, initially it was at this location, finally it has reached here, so that means it has moved r distance in the vertically downward directions. So work done by gravity we can write mg into capital R, and that is equals to change in kinetic energy of systems. So this we can write half small m into v square plus half into capital M into v square. Now capital V we can substitute from the equation number 1. We get half small m v square, small v square plus half capital M into capital V, we can write small mv divided by capital M ka whole square, and that is equals to mgr. Now from here we can write v square equals to 2gr divided by 1 plus small m by capital M. So if I want to calculate V, it becomes under root of these things. Now if I just take square out, that's the correct answer. So this is my V. Okay. Now this V will give me some more informations. If I put capital M tends to infinity, that means what? It is fixed wedge. And that is very simple to analyze. We have done these questions earlier in work related theorems. if a block is there and this is fixed, so when it will reach at the bottommost point, the speed will be under root of 2gr. And I think that's what we are getting. V equals to, we are getting root 2cr. Okay, so this part. Similarly, we can also calculate the velocity of the wedge also. Okay, so one more method I will try to explain in the next video. Method number 2. From CM frame, basically, we'll try to discuss this part. CM frame. Okay, that's all. Thank you.